The James Webb Space Telescope, the most advanced observational tool ever launched into space, has once again pushed the boundaries of human knowledge. In a recent campaign, it delivered astonishing images and data from a region lying at the very edge of the observable universe. This monumental discovery marks a profound new chapter in cosmology. It reveals sights never before imagined and offers a tantalizing glimpse into the infancy of the cosmos, a realm formed less than a few 100 million years after the Big Bang itself. What the telescope has uncovered is far more than just a snapshot of the distant past. It's a revelation that could fundamentally rewrite the foundational assumptions of both astrophysics and cosmology. For decades, the edge of the observable universe remained a theoretical boundary, a horizon, defined by the furthest distance light has been able to travel to Earth since the universe began. What lay beyond it was anyone's guess. Hubble's earlier observations took us impressively far, allowing astronomers to peer into the early universe. But even it had limitations in both resolution and wavelength coverage. The James Webb Space Telescope, with its powerful infrared capabilities, an enormous mirror, was specifically designed to overcome those limitations. And with its latest observations, it has done just that, offering humanity an unprecedented peek at the very limits of time and space. In a groundbreaking observation campaign that lasted several weeks, Webb focused on a seemingly empty region of sky deep within the constellation Phernax. From that apparent darkness emerged a collection of ancient, compact galaxies, some of them potentially proto-galaxies glowing faintly from over 13.5 billion years ago. These were among the very first structures to form after the Big Bang, existing during the mysterious era known as the Cosmic Dawn. The significance of these galaxies wasn't limited to their incredible age or distance.
What
Truly shocked astronomers was their structure and brightness. These galaxies appeared to have evolved, too massive and too luminous for the epoch in which they were found. This observation challenges the existing timeline of cosmic evolution and has sent shockwaves through the astrophysics community for years. The standard model of cosmology has held that the earliest galaxies formed gradually, over hundreds of millions of years through the slow accumulation of gas and dark matter. However, the Webb telescope's findings suggest that some galaxies were forming stars at a blistering pace, producing hundreds of solar masses per year. This rate is far faster than previously believed possible for that era. This extraordinary discovery raises a tantalizing possibility. Either star formation in the early universe occurred through as yet known mechanisms, or our understanding of key cosmological concepts like dark matter, cosmic inflation, or even the Big Bang itself may be incomplete or flawed. One of the most striking features revealed in Webb's data was a cluster of extremely redshifted galaxies. Their light stretched into the infrared by the universe's expansion. These galaxies are not just ancient, they are fundamentally different from the galaxies we observe nearby. Astonishingly, some appear to already host supermassive black holes in their cores. This presents another cosmic mystery. How could such colossal black holes form so quickly after the universe's birth? Conventional models require immense time spans for black holes to accumulate such mass. Yet here they are, cosmic giants, emerging far earlier than expected. This suggests either a radically different formation process for black holes in the early universe, or the presence of precursor objects, perhaps from an even earlier phase than what we can currently observe. Even more unexpected were the chemical signatures detected in some of these galaxies. Webb's instruments picked up signs of heavy elements like carbon, oxygen, possibly nitrogen, elements not predicted to exist so early. According to established theory, the first stars known as population 3 stars were composed almost entirely of hydrogen and helium, the primordial elements created minutes after the Big Bang. These stars were expected to live fast and die young, exploding as supernova, and enriching surrounding space with heavier elements. Yet, the galaxy's Webb has found already contained such metals, implying that at least one generation of stars had already lived and died before these galaxies formed. This severely compresses the timeline for star formation and stellar evolution, so much so that current models can't yet account for it. Adding to this puzzle is the spatial distribution of these ancient galaxies. Rather than being randomly scattered, they appear to align along subtle filaments and clusters. This hints that the cosmic web, the vast structure of interconnected galaxies and dark matter, was already forming far earlier than previously believed. This finding has profound implications. The early universe was long thought to be relatively smooth, with only minor density fluctuations that would take billions of years to evolve into the large-scale cosmic structures we see today. But Webb's data suggests the seeds of this structure were not only planted earlier, but blossomed with surprising rapidity. This accelerates the entire timeline of structure formation and compels cosmologists to reevaluate how they simulate the universe's early development, adding even more complexity. Webb's spectroscopic instruments detected faint signals of ionized hydrogen and helium. These findings suggest that the galaxies under observation played an active role in reionizing the universe, the critical phase when the cosmos transitioned from opaque to transparent. This era, known as the Epoch of Reionization, is a key chapter in cosmic history. Yet its precise timeline has long remained elusive. By identifying galaxies old and bright enough to have contributed to this reionization process, Webb provides the first direct observational evidence for a mechanism that, until now, had existed mostly in theory. Webb's ability to reach the edge of the observable universe also opens an entirely new frontier in cosmological studies, the question of cosmic variance and whether the universe is truly homogeneous on large scales. Current cosmological models assume the laws of physics are consistent throughout the universe. However, the deep field images captured by Webb suggest subtle asymmetries and variations in galaxy formation. This raises new questions. Is the universe more complex and varied than we imagined? Could early quantum fluctuations or unknown physical forces have shaped the cosmos in unexpected ways shortly after the Big Bang? These findings are far from being abstract concepts locked away in scientific journals. They change the narrative of how the universe began and evolved. If the early cosmos was forming stars and black holes at a much faster rate than previously believed, then the physical constants and forces that governed that time may have operated under radically different conditions than those of today. Perhaps the laws of physics themselves have evolved. Perhaps there were initial conditions at the Big Bang that we still don't fully understand. Moreover, Webb's unprecedented ability to look back in time has reignited questions once considered speculative. What lies beyond the observable universe? If Webb can detect galaxies at the very edge of visibility, then future instruments more sensitive and with higher resolution might uncover even older cosmic structures. Some theorists speculate that these frontiers could reveal signs of multiverse theories, extra dimensions, or remnants of pre-Big Bang structures hidden in the cosmic microwave. Background: another profound implication stems from the time dimension of this discovery. The light captured by Webb from the universe's edge has traveled over 13.5 billion years to reach us. When we look at these galaxies, we're witnessing an era that no longer exists. These objects may have evolved, merged, or ceased to exist entirely. What Webb gives us is not just a view of space, but a time capsule, a frozen image of cosmic youth. This temporal reach provides astronomers with a powerful tool to trace the entire history of cosmic evolution. One piece at a time, the technical achievement of capturing such faint and ancient light is extraordinary. Webb's sensitivity and precision are orders of magnitude beyond what was previously possible. Its ability to hold stable observations for days and weeks, while fixed on a specific point billions of light-years away, is a feat of engineering excellence. The collaboration among ground control teams, data analysts and cosmologists, and processing and interpreting Webb's imagery underscores the scale of this achievement. And as more of Webb's data is analyzed, new surprises are sure to emerge. Already, signs of gravitational lensing in the early universe are allowing astronomers to see even further magnified by foreground masses. Hidden within these observations may be the first images of primordial star clusters, or even individual stars from the earliest stellar generations, each a beacon from a forgotten time. What makes this discovery so electrifying is not just that we can now see farther than ever before, but that what we see defies expectations. The James Webb Space Telescope has not merely confirmed our models, it has disrupted them. It's forced revisions and unveiled a cosmos far more dynamic and mysterious than once imagined. At the edge of the observable universe, where light meets darkness and time slows to a crawl, we now see the fingerprints of creation etched in sharper detail than ever before.